right, thank you very much for having me. I hope you're all well rested. You're got a couple of coffees. I definitely got a couple too much this morning. Yeah, actually I'm going to talk about DarkSword, which is an iOS 18.4 to 18.6.2 exploit chain, and we're just going to take a look at the WebKit part of this. This is work that was just not done by me. It was a lot of this was done by my colleague Matthias, who is on a well-deserved vacation in Poland. So unfortunately, he's not going to be here today. But if you get the chance to talk with him about this, I highly recommend it. And it's not just me, it's the entire Verify team that took a lot of time in the early beginnings of the year to work on this. And I have my colleagues Sarah and Kevin, who are sitting on the front left, who also did some work on this. So it's a large team effort. Well, let's get into it. Today we're going to talk a little bit about how we were finding DarkSword, what's the overview of the chain. We're going to dive deep into web content code execution, especially about some of the mitigations that need to be bypassed to take this from an arbitrary read and write to get actually code execution. And we will close with some conclusions. Yeah, how did we find DarkSword? And it all started basically on the same day that we already were able to publish some research about Karuna. We had some friendly researchers from another security company that is called Lookout. And they did some pivot on some of the Karuna infrastructure, and they stumbled across a link that they sent to us, which is exactly this one. And when you started to take a look at this, we were like, it can't be that easy, right? Yeah, and yes, indeed, we started to take a look at this, and what you can see here on the screen, there's not just one very obvious part here, there's actually a couple of them. And you actually also get lots of very, very nice debug log messages that are sent to the server that are telling you exactly where the chain is, what went right, what went wrong, and where it goes to. You can't see this here, but at the very end of this chain, we're going to be looking at about 120 debug log messages. There is a sandbox escape 1, there's a sandbox escape 2, and then there's a privilege escalation, and it's done. It's very, very nicely, and you could actually just copy the entire chain by just looking it up in Burp Suite, reading the JavaScript code, and just dump it step by step by step by step. You don't even need an iPhone for that. If we're taking a look at the exploit chain itself, we have multiple vulnerabilities, multiple different components here. We have the first part, which is the web content code web content arbitrary read and write, with two different vulnerabilities. One for 16.4 to 18. One for 18.4, and then the other one from 18.6 to like going forward. Then we have a web content GPU sandbox escape, that's the first one. And then we have two kernel vulnerabilities that allow us to get code execution inside of media playback D and basically write arbitrary physical memory. Yeah, this is the first one that was fixed in 18.6. This was already done before any of the chains were like publicly discovered. It was credited to a couple of Chinese researchers. I don't know them personally. The second one is already credited to Google Threat Analysis Group, and this was fixed in iOS 26.2 in December last year. And it was also backported to 18.7.3. The interesting part here is when Google reported these chains to Apple, I would say roughly in the end of November, December timeframe, a lot of the devices were already vulnerable to this. So when we first learned about the chain and when we discovered this, we're talking about March, a couple of months later. So at this point in time, there were already multiple different threat actors that were exploiting this over a large set of devices. But the only thing that was like covered in media was the 3.55% of devices which were vulnerable at the point in time that we discovered it. But at the originally exploited time, we're talking about 0 days that were potentially vulnerable against billions of devices. This is then the TPRO or pack bypass that we're going to talk about. It was fixed in 26.3. This is the only vulnerability that was not backported to iOS 18. Even though Apple claimed they did backport it, but they never did. They just opened up some of the patches for like older devices, but this one was never fixed. The other two kernel vulnerabilities that were credited to just the Apple CR team were actually patched in November This is roughly around the time frame when Google also discovered this. The same one here, and then it was backported. I don't know why Apple never gave any credit to Google at this point in time. That is, no. And also, I also don't understand why these vulnerabilities never gotten like a designation that they have been exploited in the wild, because they had. Another thing that I don't really understand at this point in time, why Apple never backported these patches to iOS 17 or iOS 16, because some of these vulnerabilities and the kernel bug are exploited by jailbreakers even down to iOS 14 and 15. They did that with the Corona exploits after they became public, but they never did it for the DarkSword ones, which means it's great they patched all the kernel exploits for Corona, but now people can just use the DarkSword ones. I don't understand the inconsistencies there, but it's Apple's patch policy, and they will know best what they claim and what they want to do here. Good. This is the last part of the kernel bugs. This is the one that actually lets us access physical memory. The other one bug here allows us to turn any arbitrary memory into shared memory. That means we can also write to it, which is pretty nice. This is used after for like code injection. Good. Now, before we can talk about how they're bypassing some mitigations, we need to actually introduce some of the mitigations first. In older times or in other desktop operating systems, if you're getting code execution or you're trying to get code execution in a web browser, it's pretty easy. You get some sort of read and write primitive. You have JITted memory. You actually write your shellcode into the JITted page, and then you start to execute this. This is not possible on iOS because Apple started to introduce a couple of mitigations to make this harder over the last years. We're calling these XPRR, but the real names would be APRR, which is a kernel interface, and SPRR, which is the user space interface here for Unpack. Then we have trusted path read-only, and we have pointer authentication codes and JIT cache. Let's talk about SPRR. The idea behind SPRR is basically that you allow per CPU core to toggle between if memory is readable, writable, or executable, which also allows you, if you have a JIT page, that you will lock this down to one CPU core that can now write to this page and add the JITted part, but all the other CPU cores are going to see this memory still as read-only or just executable. This means that if an attacker is able to write to it, they might be able to change some part of the JITted code, but they're not able to execute it at the same point in time. It's in a first evolution of bulletproof JIT that was introduced in APRR, and it's a hardware feature that is baked into the memory. It's the same primitive that is protecting some parts like PPL or later on SPTM in like the kernel part of iOS, but this was now introduced to user space. This works by having a couple of functions that can be called. This is the older interface, where you can see there is like a thread self-restrict from RWX to RX, and then the same from RWX to read-write. And also the other function is going to be just to check if it's supported, and you will always see that there is these assembly instructions here, the MSR, with these specific registers here to spot these specific parts in code. This is a newer interface that is used in WebKit now, and it basically uses the same functionalities that we have some thread self-restricting function to get into it and get out of it again. Now, it's not just that WebKit has the JIT part that is interesting here, but there's also a second part which is non-JIT code execution that could be a problem. And so Apple also thought like we need to protect our dynamic linker a little bit more, and this is trusted path read only. The idea behind this is pretty much the same as SPRR. If the dynamic linker need to do some changes on some very sensitive memory regions, like data const segments, like interposing tuples, or like just the internal runtime state, it also wants to make sure that the same principles I can use in the kernel or inside the JIT space, I can also use for these parts as well. So I once again have a per CPU toggle where I can say like there is one thread that is able, or like one CPU core that is able to read and write to these parts, and then they do all the changes, and then afterwards they resolve it back to read only. What is very important here is that this trusted path is very fast, but it also there is no locking in between. if I would have in a thread that is running on the trusted path any sort of locking, that means I could keep these memory pages in a like read-write state, and some other thread could now start making modifications to it because it's based on the same CPU core. This is a feature that was introduced in iOS 18, which is also why we're not going to see some part of these mitigations or bypasses in like earlier versions in Corona. It's like a first thing that attackers had to bypass here. As before, we can see the same registers here that are also used. So it's also, once again, the same kind of hardware feature that is used in the CPU. And we can also see that it's the same like principle. That's a function inside of DILDs that is in the first part, first checking if the memory pages are already writable. If that's the case, they just do the work. And if not, you can see that there's a quick part here where we actually change it to read-write, we do the work, and then we change it back to read-only. All of these functions should be also inlined to make sure that there is no way that someone can just call a function if they have a pack bypass to make it read-writable, then they do what they want and then change it back to read-only. This should be like one trusted path, which is like one call that is basically going through. The last mitigation we need to talk about is Pointer Authentication Codes, which has been talked about quite some often. The basic idea is that we want to protect return pointers, jump pointers, or other pointers on the system with a cryptographic signature. And all of these different pointers are basically signed with 5 specific keys that are available on the system and a context. The idea behind the context is that you can sign a pointer that is coming from a specific function. Let's say I'm having function A, and I'm calling function B. Then if I have a specific context inside of function A, and I'm signing the pointer to function B with this, even if I might be leaking that pointer to function B, I can only use this pointer from function A. That means if an attacker is getting code execution, is leaking pointers, so on and so forth, they need to be able to call this specific pointer from function A. Because this is not always going to be feasible, and a context is not always a thing that I can use, because, I mean, the runtime is very dynamic, I also have something that is called a zero-diversified pointer. In those cases, I just don't have a context, and if I have this specific pointer that is zero-diversified, I could call it from arbitrary functions, as long as I have an ARM instruction that allows me to call pointers with a zero-diversified context. If we're looking at DLSym, which is allowing us to like resolve symbols and like sign basically pointers to it, DLSym will always return us a zero-diversified pointer. Okay. The last mitigation we need to talk about is JIT cache. This was basically done to reduce the kind of capabilities that an attacker would be able if there are that an attacker would be able to get if they're able to run shellcode inside of the JIT region. Where Apple said that it's only a certain set of ARM instructions that should be allowed to execute. There's only a certain set of APIs that are there. There is dedicated pack pointers that are just valid for the JIT region to also make sure that you cannot just easily build yourself a pack signing oracle because these keys are then not available in that specific part. So you can see here there's a JIT cache IB key, which is then used for all the pack pointers inside of the JIT cache. Now, if an attacker gets into a state where they have arbitrary read and write inside of WebKit, they can basically decide to go 2 different routes if they want to get to code execution. They can try to target SPRR and JIT cache as mitigations to get code execution inside of the JIT part, or they can decide they want to bypass TPRO and pack in order to get code execution outside of JIT. In earlier times, people were always trying to target the JIT part. The attackers for DarkSword decided that they want to go and bypass TPRO and pack. So what we want to do and what we want to achieve here is basically being able to call arbitrary functions in WebKit or WebGPU, in WebKit in order to launch our next stage of the attack, which would be a sandbox escape into the WebGPU process or some of the other associated processes. or even launch an LPE if you have a kernel attack surface that is immediately visible. We don't need to be able to call arbitrary shellcode. It's just enough if we have an arbitrary function call with whatever is available inside of the WebKit context. So the strategy that the attackers try to do here is the first thing that we need to find is a zero diversified function pointer that allows with a BLR AAZ from a writable memory construction that allows us to call this first function. Then we want to construct a job chain that allows us to bring us from one function call with one parameter into that we can have an arbitrary function call with 3 parameters and 6 parameters. If we have a function call with 3 parameters, we can call a function like dlsim and get as a result back a assigned pointer, so we can also call other functions. If we have a function call with 6 parameters, we can run and create our own thread. And then we can also define the context, and after this we basically have arbitrary code execution, even native one. So in order to do this, we need to find the first function that allows us to do the function call with 1 parameter, then go to 3, then go to 6. We need to be able to call dlsim, and we need to be able to then sign pointers with arbitrary keys, with available keys in arbitrary context, and then run the threads. Now, the first part that they used for the job chain trigger is a function that is called ddfa scanner first result in unichar array. And we're going to take a look at this a little bit more in detail. What is important here is this function is soft linked. Soft linked in the case of WebKit, in case of DILT, means that the function pointer itself is not resolved at compile time, but it is resolved back at runtime. That basically means that when you try to load this function, DILT is going to know, oh, this function pointer hasn't resolved yet, and then it's going to sign this function pointer with a zero diversified context, and it's going to write it back so that you can call it, which is a good thing for us, because that means that this function is always going to be behind a zero diversified pointer, and we can, after it has been resolved, easily call it. This function is reachable basically from content document write. It goes into like 16 functions deep. And there is a telephony number detector find function that is called before. If we take a look at the find function, then we can see here, sorry, this is not great readable, but it basically takes the first result, it's going to call the, scanner first result unique array function. Then it has another function called the phone number scanner. And this function is going to be returning us basically an attacker-controlled part into x0. So that means after this, I have a function pointer that I can resolve, and I have x0 as an argument that is going to be called here first, which gives me our first primitive that allows me to call basically an arbitrary function if I have a signed pointer. If we're taking a look here at, this is the DDR function here, then we can see here this is a call that goes to the phone number scanner. Then x8 is attacker's control. This is always going to be at a known offset, which means at the very end, if I have a known offset, it's not going to change. If I have the offset for this specific version of iOS, I know where this part in memory is always going to be located. So if I have a read and write, I can basically control this. And at the end, we're going to see that here is the zero diversified call to x8, and x8 is attacker controlled, so that allows me to write the function pointer there and jump. This here is the telephony number functions, which we can also see that it nicely takes x8 as an argument as well. And once again, this is as a fixed determined location. And then at the very end, we can see that this translates from x8 at an offset, and it goes back into x0. So this is perfect for us because it immediately allows us to ship something from location x8 that we control at a fixed location into x0, so we can basically use this as a function call. Okay. So this is what the attackers needs to do in order to trigger the job chain and control this. The soft link pointers that are going to be resolved are going to be stored in data dirty. this is a region of memory that is not protected by TPRO. So as an attacker, once I have arbitrary read and write, I can basically control this region. I don't need to bypass any other mitigation. And then the phone number scanner's value, this offset is inside of the data region, so I can also write to this, and this is basically where I get control. There is another function here that is getDisplayType, that is also soft linked, that is used a little bit later in the chain. So what allows me this basically is I write my function pointer into one part, and then I have the buffer pointer to my job chain in the another part, and then I can use this function in order to call it. The next part of the next part is a trampoline, which we want to use in order to call other functions with 3 and 6 parameters. This one is located in the libgpu compiler implementation lazy dilib section. And what we can see here, it starts with x0, and then it basically calls that into x8. And then here it's going to do a branch for x8. So we can use this in order to go from x0 and call another part into x8. And then if we're using it a couple of functions later that they're using, we can see here that this is also coming from x0 into x19. And then later on, there is 3 different arguments here, x0, x1, and x2, which are going to be coming from x19 with the offset. And then we have a branch to this part here as well. So this allows us to call a function with 3 different arguments. And this is another function that they found that basically works with the same principle. I once again start from x8, and then I have x19 that comes from x0. And from x19, I have 6 different arguments here that are coming from various offsets. What's important here, both of these are having here a pointer that is called from an object that is gsecurityD. We can see this in the previous slide here as well. So if I have a chance to create the structure gsecurityD, I have perfect control of the pointers that are going to be called next. And I also have a way with my argument x19 that is transported over as x0 that I can also control the function parameters here. So if we draw this up, this looks basically like I start first from my scanner, then I use my GPU compiler trampoline, and this allows me to have another call into x8, and then from x8 I can have my gsecurity object that contains the other function pointers, and x0 is always going to be used as the first argument, and then from x0 I can read the other arguments, and x0 in this case is my buffer with the other parts. So we can use the first part of the job chain in order to call dlsym, dlopen, and sign pointers, and we can use the second one in order to run pthread create. There's one small problem here. All of these functions are going to taking like 0 diversified pointer, and the question is, where do we get these 0 diversified pointers? Because we need to have some sort of mechanism to create those in the first place. The soft link function that we use in order to get the job chain running in the first place has one problem. Soft linking works only once. That means after this is resolved in the first place, there is no other chance that I can resolve a second pointer. I would need to find multiple different other functions that are also soft linked in order to do this. But the attackers found something else, and this is already something that we had yesterday in your talk, and this is interposition tables and tuples. So this is a feature inside of DIL that would allow you to change some part of the behavior of libraries and functions, where if you load a new library, you could say, like, I want to interpose some of the functions inside of this library and change their behaviors. So if DILD is going to see that a library is loaded and there is a interpose section inside of the mach-o, it's going to take a look at this interpose table, which is going to have basically a function and a replacee. So if the attackers are able to write to this interpose table when a library is going to be loaded, then they have a way that they can basically get arbitrary function pointers signed. The only problem with this interposing state is that this is protected by TPRO. So in order to get there, attackers need to have a TPRO bypass. But let's take a look how they actually get the zero diversified functor from the interposition table first. There is a very nice function inside of the IO image framework, and this is IO load CM photo symbols, which is going to do a DL open for CM photo, and then it's going to resolve all of these functions here with like a DL sim. So if we have a chance that we can write interposition tuples for all of these different functions, we can basically control the other functions that we want to sign ourselves. As interpositions are also something that is called once in that case, this would allow us to basically generate the state only at the beginning after this library is loaded. But if we can basically create sign function pointers for DLSIM or some of the other primitives that we want to have, we get our zero diversified pointers. Yeah, and this is how the interposition table should look like. These are the three functions here. This is our trampoline. This is the first function that allows us to call 3 arguments. This is a function that allows us to call 6 arguments. And then we have DL open, DL sim, and sign pointer. And this is the IO load CM photo symbols, which is the initial part, like initial function that allows us to resolve all of these symbols. Yeah. So once again, this is a soft linking feature. I've talked about this before. Now let's take a look at how this job chain works. We start once again here in our first primitive that allows us to call one function pointer that is already zero diversified with 1 argument. And this is the init MA capture appearance get display type. This is the second function that we're writing in the data dirty section in the beginning. So this function then allows us to get a function pointer via the soft linking feature for this part. And then it goes over into loading the IO load CM photo symbols, which is going to interpose all of the other pointers. And then after this, I'm also going to include this into my interposition table as well, so that afterwards I have all sign function pointers to recall it all the time. Okay. So at this stage, we basically have most of the primitives already available. So we have a function that allows us to call one zero diversified pointer with 1 argument. We have found job chains that allows us to call 3 and 6 arguments, functions with 3 and 6 arguments. And we also found a getJet in order to create zero diversified pointers with our image.io gadget. Now, the only problem that we still need is we need to have a way that we can actually write to these interposition tables. And now this is where the TPRO bypass comes into play. Okay, this is going to be a little bit more complicated. Okay, so what the attackers here need to do now, they have basically 3 different threads that are going to run. They're going to start here first on an attacker's thread. And then there is going to be a mutex that they found. And this mutex is one of the mutexes that they can write with their arbitrary write primitive. But it's also a mutex that is respected if DL open is called in a function like run initializers bottom up. So this is what I mentioned first in a TPO bypass. You need to be really, really sure that you don't have any locks or any blocks that would allow you to like stop a thread if it's going on. So the attackers found one of these parts here so that they can block basically this thread if it's still in a read-write phase. So we start first by setting the mutex, and then we have a bitmap object, and we're going to running close on that bitmap object, and we're going to trigger the DL open. Now, if we're using bitmap close, then this is going to be opening up a specific library for a specific allocator object in order to run the deallocator for that specific bitmap part. So this will trigger the DL open, but because we have set the mutex, the DL open that is going to stay in a locked state, but it has unlocked the TPRO region for us from read-only to read-write. Now we're going to take a look at our thread and to find the specific allocation vector for this object. Now, this allocation vector, once we have found it on the thread, we're going to construct this in a specific way that once the allocator free function is going to be called on that object, that we get into an arbitrary write state. The only problem we have is we cannot directly write to the TPRO region from this thread. We can only write to it from this thread because of the design of the mitigation. So we need to make sure that we allocate something that we have control of, and then the allocator free is going to do the controlled write for us. So once we have mutated and changed this allocator object, we will unlock the mutex. Then once vector resize 0 is going to be called, this is going to be result in a trigger to allocator free, and then this is going to be writing into the first part of the interposition table, and this is the buffer part. Now, the interposition table has both a buffer, but it also has a size field. So we need to basically write two parts here. But our primitive only allows us to do this once. So that's why we're creating another lock here. Then we're going to run another object for like a bitmap, and we're going to run another close, which will trigger another DL open part. And in this case, we basically do the same things again. We're, in this case here, we have triggered this other DL open. The lock is still going to hold this thread now once again in a read-write state. We once again look for the allocator object. We corrupt this object. And then we're going to unlock the mutex again. And once the vector is going to be calling a resize 0 again, we can use our write primitive again. And this time we can write the size. After this, we have basically used this trick in order to write the interposition table into the state that we have the buffer and the size, which is correct. And in both cases, these threads that were actually changing the TPRO region from a read-only to read-write were doing these specific writes for us. I know it's a bit complicated.
Is this separate from the last slide? Like
No, sorry, it's the same. It's just a very large. So. So this part here is what is here. It's just going through. It's just, the format doesn't allow me to get it all into one timeline. Good. This is the allocator free function, where we can see here is the allocation metadata object, where we can see it's coming from a pointer, and then we have an offset here where it's going to be written from. So once we find the specific part inside of the stack, we control this part of the offset, and then we can write allocated bytes into it. Good. Now, this allows us to have basically all the primitives that we need. Now, we have a TPRO bypass that allows us to write the interposition tables. And with the interposition tables, we're going to get our zero-diversified pointers that we need. And with the job chain that we have built before, we can now arbitrarily call DLSym, DLOpen, and pthread create. And this is all we need in order to access all the native functions that are available from the WebKit content. And basically, this is an arbitrary function call now that allows us to start the other parts of the chain. Good. Now, what did attackers do with this? They basically were using two additional kernel vulnerabilities, and we're going to talk about this at another point in time. And these two kernel vulnerabilities allowed them to turn arbitrary physical memory into shared memory, which means with the shared memory, they could change other processes on the system. They could create a thread in these processes, and then they can basically also load other libraries. And what they did here is they were basically reusing some of the primitives they already had in WebKit and decided that they're going to use these other processes, open up JavaScript core, then load another WebKit part, corrupted this WebKit part into getting another arbitrary code execution part into that process, and then they were basically starting the entire chain that they used in the first RCE just inside of other processes to get code execution there. And then they were basically just loading arbitrary JavaScript and executed that in this process, which is a very smart thing to do in this case. Because normally if you would be attacking iOS, and what we've seen in Karuna is that people in order to get arbitrary code execution somewhere else, they need to bypass a lot of the mitigations that Apple added over time, like the code signature bypasses, like SPTM bypasses or PPL bypasses, kernel pointer authentication codes, so on and so forth. Now, with this trick, because they could take it into shared memory, they just get code execution in other very privileged processes, and they completely are sidestepping all of these mitigations that Apple built up over years to make it harder. Corona had bypasses for all of these, which made it also very expensive, but the attackers here just used these very, very nice tricks in order to completely avoid this and still get the job done. Now, they were basically having one specific implant that was running inside of Media Playback D, and this implant was orchestrating now different parts. We have a keychain copier part that was running inside of config D or security D. We have two Wi-Fi passwords dumps inside of Wi-Fi D and security D. We have an iCloud dumper inside of a user event agent. And then we have a file downloader that runs inside of Springboard. And with that, they were basically extracting a lot of very, very interesting databases from the phone. If you want to know what all databases were and what you can do with that, you need to go to Sarah in one of her forensics classes, because it's basically everything that a forensic person would want to take a look at, but it's also everything that an attacker would want to get from the phone. It allows you to completely create a pattern of life for this person. So like all iMessages, all passwords, authentication tokens, up to even databases of what a firm was doing there, like a health database, so on and so forth. It's really, really a lot, and we have a full blog post on all the different parts. Then all of this data was afterwards copied locally on the disk, and then the file downloader part here was also responsible for taking all the files from the different places and uploading this to this C2 server. Good. Yeah, some of the IOCs that we have seen here, and these are very obvious IOCs if you have visibility on the system for these specific directories, like keychain 2 inside of temp, Wi-Fi passwords inside of private or wireless, iCloud dump, so on and so forth. Some of these IOCs are in multiple different places. Sometimes, even if the first place might not be writable in the function, they decided to use a second location. Some of these locations are also getting cleaned up afterwards, but some of these locations are not. So if you have good visibility of the system, you can still very easily check for compromises in there. What we could also see in the framework was that it seems to be having used way earlier. Already in 17.4, we could see some parts that were used in 17.4 or 17.4.1, but they were not used in the specific chain, but it looked like something that the attackers were just reusing their approach over multiple years. What's also important to note here is when we took a look at this specific part of the chain, there was no OPSEC. So I just took a phone, I run burpseed on it, and I basically started to step by step dump all the different chains and taking a look at it. So this took me 15 to 20 minutes, reading all the parts and getting the different stages. There was no timing checks. There was not making sure that I'm not using VPNs, proxies, or other parts on the system. It just basically allowed me. You have seen that some part of the URLs were very descriptive, like RCE loader, worker, module. This is not what a, let's say, more professional threat actor would normally be using. We had verbose logging in both on the network side, but also a lot of these steps were all logged to unified logs, which means if you also have visibility of forensic evidence afterwards, you could see this. This file-based IOCs and TAM, there's almost no cleanup that has been done. This part, so this version of the kit did clean up in one of the two locations that have crashes, but they forgot to clean up the second one. Another part of the implant that Google found cleaned the other directory, but forgot to clean the one that this one cleaned. So there's a lot of behavior here, which is very interesting to see that attackers are using this without basically non-OPSEC at all. There was no additional encryption that was introduced here, so if you have some network interception capabilities, you could easily see and read all the traffic. Some conclusions on the WebKit side here. Let's say the first part here is some part of the OPSEC and proliferation consequences. Sorry. Okay. This specific part of the OPSEC has some very profound consequences on the entire, like, say, offensive industry. Now, because the OPSEC was so shitty, we tried to really, really make sure that once we start disclosing this, that all the domains of the attackers were taken down. The reason for this is all JavaScript. Every one of you in the room can basically take up a web server, capture the network traffic, and get this chain going in like 10 to 15 minutes if they wanted to. That's why we wanted to make sure that this is not able to proliferate, because even at the point in time that we were like capturing this, we were still like 250 million devices vulnerable. But unfortunately, a couple of days after we've published this, someone disclosed the entire chain on GitHub. And now what we're seeing is basically the same as Karuna, that attackers are now copying this and using it against multiple people. Some of these attackers are now using a little bit more OPSEC. They're not calling it RCE loader anymore. They're just calling it like a random string. But it doesn't change that the same like behavior is still possible. We are also now seeing attackers that are combining Karuna and DarkSword into this. And because this was so easy to copy, we're now in a state that iOS exploitation is not just for, let's say, some privileged offensive actors anymore, but any, let's say, standard criminal that has some deployment expertise can now start building up these chains, of course, only for the vulnerable versions of iOS. But even up to today, at least in our telemetry, we're seeing people that are running these vulnerable versions and are getting infected. There's the same with Karuna. And because a lot of these techniques and bypasses were kept like private for like the offensive industry, now a lot of people that are coming from a Windows, Linux, or even Android background then can now understand how to learn and bypass some of these techniques on iOS. And so far, we haven't seen that there like TPRO bypass that is used here, or these strategies that Apple did start to mitigate some part of this. So if people have now other vulnerabilities inside of WebKit or other cases, it's way, way easier for them to like build up chains. The same with these strategies that we have seen in just injecting JavaScript into other parts. Now, a simple kernel read and write vulnerability is now enough in order to get the job done. I don't need the advanced kernel parts anymore. And finally, if we're looking at some of these more advanced like AI tools or like models like Mythos, they're now way, way easier or helping people to like really lower the burden into getting some part of these exploitation going. So if I can find some of the bugs easier, if I now understand how the techniques are used and I can even train my models on some of these techniques, it's kind of a real game changer in what we're going to see in iOS exploitation going forward. And on a detection side, we're kind of still lacking the frameworks that we would see on other desktop system, or like Android, like Google introduced intrusion logging on Android in order to like tackle some of these problems. But on the side of Apple, they decide to basically that there's a company that is able to protect everyone from kind of these threats. And what we're seeing over time and time and time again, it's companies like Google, like organizations like Amnesty, Citizen Lab, it's iVerify that are finding these threats in the wild, but it's not Apple that is finding these patching systems telling you about this. So we're in a state that I'm very worried about what's going to happen in like iOS and maybe even macOS security over the next coming of years. And I'm not sure if Apple's strategy is still like valid enough that we can protect everyone against like larger mass scale attacks, especially with people not just patching on like day one if something is closed. Okay, sorry, that was just some part of what changed in March. Now, there's another part here that I want to talk about, and this is the effectiveness of software mitigation. As we have seen, some part of the root causes of the bugs that we have in arbitrary read and write part is the further we get away with some of the mitigations on what we're trying to close, the harder it is to actually have these mitigations being effective. It's increasingly difficult for like Apple or even other like defenders to build up mitigations that can stop someone that has already like arbitrary read and write to get from there to like code execution. You can make the way harder. You can basically stop some of the techniques, but it is super, super hard to make the system completely so isolated that this is not possible anymore, especially with something like a DIL shared cache, which allows you like to access functions which are like 2 GB in like size. I don't think that this is going to work, and we would always need to expect that someone is able to get from the first stage to the next stage. Privilege escalation is a different story here, but this specific part, it's just a couple of hurdles more. Yeah, and for the specific TPRO bypass or like the soft linking issues, this is definitely a good target where Apple could easily just include some part of these sections into the TPRO stage, because the soft linking part is a very, very easy for an attacker to overwrite. Yeah, if you're interested in some more material, these are our amazing talks just about how PAC works. This is our blog post that goes a little bit more into the details of how we found it and some of the IOCs. This is a great talk into understanding how WebKit mitigations works. Same as Quentin's talk here. And obviously, if you want to understand all the mitigations and what Apple has added over the years, Jonathan Levin's talk just a couple of months ago from OBTS is an amazing resource. And the Guza was the first one that detailed APRR. Yeah, and as always, there's multiple people in the community that already did like lots of work previously. Yeah, and this is, we called this Black Ladder Bear first when we found it, and then we chatted with Google and saw that they found it too, and then we called it DarkSword together, but let's say I still like this. Maybe one funny story at the end. We chatted with because this chain was used in Ukraine to target Ukrainians. We chatted with the Ukrainian CERT to make sure that they're taking all the domains down and like gave them basically a pre-read. We also sent them a logo with like some bears and a dark sword that we wanted to use. The only response we got from the Ukrainians was like, great blog post, thank you. But can you please make sure that the bears are looking miserable? All right, thank you very much. Any questions? Sorry.
You mentioned a bit about where Apple probably shouldn't be investing in these software mitigations because they're not as effective as they might be. But I guess two parts. Like first on what's the economics from the attacker side? How much did it cost to get around everything? And where should Apple be actually investing to protect?
I'm not sure how much it took the attackers to find some part of these gadgets. I mean, the interposition tuples is now something that is obviously like public, but you found the same thing in your talk just by looking at a different part. So I'm not sure how much the costs were. I don't think that Apple should invest so much in more mitigations over time, but thinking more about how do we actually detect attackers that are on a system so that we can spot the devices that are attacked and we can learn more about how the attackers were going in, rather than spending more time on like mitigations. But that's, I mean, I've been working in enterprise security for like 10, 15 years, and like 10 years ago, we have learned a lot that we were not able to be going to be stopping attacks all the time, so we need to better understand how attackers are like getting in, and then use the detection part in order to like learn where our gaps are and then fixing it, rather than spend all the like resources on prevention.
Thank you. Really amazing talk. Also cool to see that swapping function pointers also works in the real world. When I was looking through stuff for my talk, there's a very similar way that they create essentially shared logic that's going to be shared by all of Rosetta called AOT shared. It's not the same as putting all the dynamic libraries that macOS is going to use into the shared cache, but it's similar in that like it's essentially all the logic that runtime wants to use. And I found it really difficult to figure out any sort of live or dynamic analysis for it. It was very static, you know, looking through like IPSW or OTool and just kind of begging that my grep skills work. I was curious, was there anything in terms of like, live debugging or analysis that was especially useful for trawling through those really big files for specific function calls? And I'm saying that because I don't know any current tool set, or I'm not comfortable with one.
I mean, as you can see on the slides, that's... no. Come on. We're a huge fan of Blacktop's tools, too. And much props to him. No, I don't think... we also use a lot of static analysis. Most of this research was done by Matthias, and it works pretty well. But he's also a very seasoned WebKit exploitation developer, but also finder. So he does this for 10 years. So I can't really tell you more about his techniques, but if you get the chance to talk to him, you might be able to answer this a bit more.
That's all good. I'll make sure to stay literate. All right, thank you.
Some insight from Itush from our team, Binja. A little bit of a plug there for Binary Ninja. Just putting it out there. So previously we talked about there being an orchestrator, and then some components between different processes. Why can't one process be responsible for all of the collection, and why do they have to be orchestrated through shared memory in order to collect different components across iOS?
Yeah, that's actually a great question. So the problem here is that they don't have this SPTM bypass in the kernel. So they cannot just create their own process, give it arbitrary access rights, change their permissions into running as root and unsandbox. So that means they need to leverage existing processes on the system that already have these kind of permissions. So that's why they're using, for example, Springboard that has access to a lot of files on the system in order to read the files and upload them and has network access. Or they're using Wi-Fi-D and SecurityD that can already access your Wi-Fi passwords or your passwords inside the keychain. If they would wanted to extract, let's say, data from WhatsApp, they would need to inject into WhatsApp in order to read the WhatsApp passwords or find another process on the system that already has this kind of privileges. But I'm not sure if it really matters in that case, because the user space part of the system already needs to have all the permissions in order to allow you to use the phone. So you just need to find the right process, inject to it, and then you do what you want. Obviously, this is also nice to build up some detections. If you will ever find Springboard with JavaScript library, JavaScript core loaded into it, this might be a very obvious case of something's weird going on the phone.
Last question.
One more?
I'll do it with no mic. So Apple offers lockdown mode, and I'm curious if any of the exploits that you talked about have successfully been run through lockdown mode, and then also having an iPhone, being a daily iPhone user, what can the average person do if they don't want to go through the lockdown mode process to mitigate some of that risk?
Great question too. Lockdown mode would have been able to stop some part of the attack, but the kernel exploits, for example, would not be like a part that is mitigated by lockdown mode. But a part of the initial remote code execution would have been stopped by lockdown mode. I wouldn't say that there is no bypasses for this. It's just I don't think that a lot of people are already using lockdown mode enough that attackers have an incentive or mitigation to go after it. It's just even most of the targeted persons that we are working with are not using lockdown mode. What you as an individual can do is make sure your phone is up to date. Make sure that if an update is available, that you're also installing it basically on day 0 or day 1. And then there is tools like Verify. There's other organizations out there that in case you're more targeted and you want to get your phone checked on a more regular basis, then you can work with these organizations. We have a consumer application that allows you to run sysdiagnosis a couple of times per month, send the sysdiagnosis to us and get a check. But I don't want to do much advertisement for us here. There's other organizations out there that do the same thing. Like Amnesty Citizen Lab did a perfect job over the last years in catching some of these advanced attacks. If you don't want to use lockdown mode, there's other ways that you can lock down some part of the system. But I highly recommend do not stay on old versions of iOS. This is going to get very dangerous in the next couple of months and years. Okay, I think that was the last question. Thank you very much. See you later at the bar.